Okay, you can go ahead, André.
So, good morning or good afternoon for everyone. So today we're going to talk about local resolution of singularities. So the plan is to, well, I'm going to start right away stating what is the theorem that we're going to prove. And then today the plan is to go over maybe 75% of the proof, like the main tools that we are going to use, and to finish on Monday. That's the plan. A couple of things about the proof that I have chosen. It's not the, there's another microphone on. Maybe we can, maybe we could cut the microphone on. So the proof that I'm going to thanks. If there's any question, please interrupt at any time. So indeed, so the proof that I'm going to do is a little bit heterodox. It's not the usual one that is done for local resolution singularities. And the reason for it is that I'm actually going to take the proof that we do in our monomization result, which is the next technique that I'm going to talk about. And I'm going to do it sort of like the zero case, which is for functions. There's no morphism here. The morphism is going to be just a constant morphism. And I'm going to reproduce the exact same, like the same ideas of that proof, but in this context here, in a more simpler context of resolution of an ideal. Okay, so that's the plan. So I'll start by saying here, what is the theorem? So let Q be a quasianalytic class. And we start in the same way. M be a Q manifold. E containing M is a simple normal crossing divisor. And we take an ideal I in the quasianalytic class and privileged. Right, our objective is to make this ideal monomial by blowing up. So in this case, we're going to do local blowing up. So the way that I'm going to state it is going to be local in M. So for every point B in M, there exists a neighborhood U of B and a finite family of Q morphisms. I'm going to give here some sort of name that I'm going to use throughout E lambda, which will go to U, E restricted to U, which is contained after all in E, such that maybe I should write here lambda some index set. I just said it is finite, but let's put it on the board anyway. Such that, and three conditions that I'm also going to use from time to time with their numbers. So it's three conditions that I'm going to hold kind of everywhere. So the first thing is I'm going to tell what sigma lambda are. So sigma lambda are composition. No, sorry, it's a finite sequence as well. Is the composition of a finite sequence of local blowing up. So recall that local blowing up for us just mean made a blowing up and an open immersion, for example, to restrict ourselves to one of the charts. Actually, this is the main case of a local blowing up. Make a blowing up, restrict to a chart. That's or to a very small set, open set of one of the points on the chart. These are the two main examples that we're going to follow. Two, we want this to be a resolution of singularities, not only a avoidance of singularities. So we do need some extra property, some global property of it. And the one that we have is that it's semi-proper. So sigma lambda is a semi-proper covering. View. So just to point out, that means that if we define the morphin sigma, which goes from the disjoint union of the V lambdas to U, where this sigma restricted to V lambda is equal to sigma lambda, it's not supposed to be here, then sigma is semi-proper as we define in the next lecture. And third, and what we want from here is that for every lambda, the pullback of I is monomial. So we have indeed one. So 1 and 2 are the conditions on the sequence, and 3 is just going to be that the result that we want to get after all, that this guy is going to be monomial. I will enjoy here to provide a definition of something that I'm using here, and it's not a problem when I'm talking about a finite sequence of local blowings up. Oh, let me add compatible with E. It's not a problem when you use local blowings up compatible with E. That's when the situation that we defined that this morphism had a property over the divisors. We were able to write like pairs like this, but in a more general setting, we can also write this for arbitrary morphisms if the exceptional divisors do satisfy an extra property. So let me just write this, or we're going to establish this notation. So if we take D in M and E in N, normal crossings divisors, we say that phi from M to N is compatible with D and E if the preimage of the divisor in the target, E, is itself a simple normal crossing divisor contained in D. So the case of blowing up is exactly that, right? We take the previous exceptional divisor, we pull it back. It's a strict transform, it's still going to be a simple normal crossing divisor. Of course, we needed a condition that the blowing up was compatible with the divisor, right? That there was no tangency point. Otherwise, this property is going to be lost. And in this case, we denote I from MD to N. So this is, I just enjoy to give this as a more general definition of what this morphism is always there, supposed to mean. So this is the result that we want to prove, and maybe just a drawing to have an understanding why it's so important for it to be semi-proper. Right. The idea is that we are going to start in our M. We're going to have our point P, and then we imagine that we have made a local blowing up. We made a blowing up and we restrict it to a chart. Then what happens is that if you consider a little box here, then some compact set, then the projection through this local blowing up is going to be like a section like this. So it won't cover everything. So the idea is that we need to take enough charts, I do not know how many, but enough charts, such that if we cover by more terms, then we will eventually cover an entire neighborhood of that point. So this is why I said that semi-proper is the difference between resolving the singularities, so covering everything, and just avoiding the singularities, right? Covering, like, if the problem was in the direction that is not containing this wedge, then we will just be avoiding it. Not what we want to do. We want to really cover everything.
Sorry, André. In the definition of compatibility, you don't require the image of D to be a subset of E, because the notation induced me to believe in. Okay, so you don't require this.
No, no, like, okay. You can imagine that this could have been empty, and I just made a blowing up, and I want to do now the exceptional divisor there.
What could have been empty? E could have been empty. Okay.
So I want to include that case tree.
Okay, thanks.
Okay, so now the proof of the result of the local resolution. I'm going to do it kind of in three steps. Like, there's going to be three parts that are well, all of them related. And the first one, I'm going to introduce combinatorial techniques. Then we will provide inductive statements. And then we're going to make a little bit of log calculus. And with all of these three, once we have all of these three things together, then it's going to be we're going to see it's not going to be difficult to finish the proof. So the plan for today is actually to introduce these three techniques. Let's see of like at least the first two, possibly the third plan, and then in the next time put everything together to prove the result. So let me start with one. And here I will consider like the topic, right? Combinatorial technique. So it's going to be very important to consider the exceptional divisor E. It's going to be all based on this exceptional divisor E. So let's fix once and for all a coordinate system. So let A be a point in E and consider an E adapted, what do we call E adapted coordinate system. So what did that mean? We wrote it as UV, U1, UR, V1, Vs, such that at least locally, these are the problems of the product of the U equals U. So the U's are the exceptional variables. These are variables that are not exceptional. We fix this notation once and for all. And now the object that we're going to look at, and to make things simpler, I decided to give them a name. It's normally in the literature, it doesn't have a name particularly, but just for to make things simpler today, I'm going to give it a name. I'm going to call it a combinatorial ideal. So we say that a privilege ideal is combinatorial if for every point A, the stack, the generators at a point A are actually given by monomials, MD, where MK is u to the power alpha k, where here we are using the multi-index notation. So here, u1, alpha k1, product, ur, alpha kr, alpha belongs to nr. I'm going to establish this, and this is kind of my first goal is to look at these ideals here and to provide a local resolution singularities for them. Okay. And this we're going to do via combinatorial methods that is going to depend on E. But before entering on what are going to be the blowings up that we're going to do, I just want to introduce a little bit more notation that anticipates this log calculus and which is related to the combinatorial part. Okay, so I'm going to consider, right, I just wanted to do this little remark before introducing something else. So being combinatorial, is a local property. Right? If you are combinatorial at a point, then there certainly exists some open set U where you're going to be combinatorial at every other point A prime. May be generated by another number, but also by monomials too. The first little remark, it's an open property. And now let's look at this is the object that we're going to look, but let's use another tool. It's going to be the differentials that are tangent to the exceptional divisor. So we denote by dE. The extension of it would be derivations over m minus log v. So the sheaf of k modulus of logarithmic differentials. Actually, not differentials, derivatives. Derivations. Yes, that is correct. So locally, and this is maybe the point here, if you look at this talk at a point A, this is going to be generated by this pen of derivatives of this one, U1, G1, UR, UR, dV1, dVs. So it's logarithmic in respect to E. We call it logarithmic, right? The reason why it's called logarithmic is that if you do this, we can see that this is equal to U over U, and which is equal to 1. Just a little remark. That's why we call it logarithmic. And so it means that the exceptional variables here are going to always be the derivations which come with the U in front of them. Okay. And yeah, before even I'm going to give examples of how this is going to interact with the ideal, but I want to define right away one operation that we can do with this, with an ideal. So we denote by dE of I. So we are going to make an action of the derivations that we have in this sheaf over an ideal sheaf I. So the ideal sheaf locally generated by so the again space, I think I need it, d of E at a point A. So in here, I'm just going to use this notation. This is a notation to say I'm restricting to the germs at A. So instead of like taking here a point A to talk about the stalk, I'm just saying this for stalk at A. This is going to be, again, the ideal, even not Oh, now it doesn't work anymore. Oh. Sorry, it's going to have a little. I cannot make mistakes anymore. For some reason, I blocked from time to time my eraser. Okay, I won't make mistakes anymore. That's my standard now. So it's going to be the span of xf, where x is a derivation, and f is in the stock of the ideal at A. Okay. So I'm going to take, and this is going to denote this ideal here generated by everything. Okay, so now that we have these two things, let's see a couple of examples of what is going on here and why we are choosing these derivations in particular. So one of the things that is of interest here is that if we take I a monomial ideal, then this derivation of E is again going to be, maybe I'm going to do a small thing, and I'm going to add I. This is going to be equal to M. And I'm going to see why I'm adding I a little bit later on. But the idea here is just that all of the derivations that we have, they are taken in such a way that it's going to leave the monomial invariant, right? If we take UK duk of M, this is nothing but alpha k, the k entry of alpha times u alpha. And if we take dvkl of M, then this is equal to 0. So from these two observations, we see that, of course, the of I is contained in the ideal I. So I summed with I just in case we needed to well, just in case. So it's just one little difference from the usual case. If, like, just to take away a pathological case, if M was equal to 1 and R or S equals to 0, so if there was no derivative in respect to V, then dE of I is going to be different than 1. It's not going to be equal to 1. So this is a little detail that can happen. And if you take all of the derivatives, this never happens. You can just use all of the derivatives, then the derivation, not the only with logarithmic respect to, if you take all of them, then the derivation of I is always containing I. But in the case of logarithmic differentials, you can imagine situations where this is not true. Here's one case. Yeah. And of course, the second situation that is kind of follows in an easy way from this example is if I is combinatorial, then dE of I is again equal to I. We have left everything invariant. So if you want to see something which is not invariant, then we're going to use the variables V. So for example, if if I is generated, say, by V1 square plus U1 square. What did I took there? No, U alpha. Then we can compute this. We can compute these derivations, right? We can compute all of them. And in here, the derivative in respect to V, I'm definitely going to include V1. So let me just note this. Easier to just note it. Note that dV1 V1 square plus U alpha is equal to 2 times U1. And if we take any of the derivatives with U, then we're going to appear here U1 U alpha. So it's not difficult to convince oneself after looking at these two computations that dE of I plus I in this case is equal to V1 U alpha. And if we repeated the process, then we're going to get a unit here. It's going to just be 1. So we're going to finish with just 1, nothing else. But one of the interesting things about this is that we're not changing the order of the monomial. The monomial in U does not change the order, it's preserved. It's the order of the other variables that is going to change, and this is going to play a role later on today. So now another definition. So we talked about combinatorial ideals, just a name, it's not in the literature, but it's a name that I'm giving to these ideals. We talked about the sheaf of derivations, that is something that has a name, the rating sheaf of derivations. And now we also talk about what are the blowing ups which are interesting to us, which we're going to call combinatorial. So we say that a blowing up from M tilde E tilde to ME is combinatorial if the center C of E is an intersection E J apart, which is in a index at J, where I recall that E was an ordered collection here of irreducible components. What was the letter that we used the other time? I think it was the EJ is an irreducible smooth component. And this index at J is simply a subindex of 1D. Right? So we're taking blowing ups where the center is just intersections of this guy. So locally, the center C is given by, well, a part of our change of coordinates here, apart from reordering U are given by the zero locus of U1 UT, where T is small or equal to R. So of course, it doesn't have to be U1, U2, U3, U4 up until UT. It could be, for example, U1, U3. So that's why I'm saying that apart from reordering, apart from changing the order of them, we can always suppose that it's just the first T entries, for example. Right? But it's just some of the intersections of these exceptional devices, nothing else. So this is what we're going to call combinatorial. Maybe I'll leave you here as an observation, as it's going to be done as an exercise. If I is combinatorial, and the blowing up sequence is also combinatorial, not sequence, just up blowing up. Then the preimage of I is combinatorial. So it's again generated by some finite number of monomials. You can just verify in an easy way that the pullback by a combinatorial blowing up of a monomial is again a monomial, and this is going to give you the result. At every point, right? So you have to make translations too. So you have to join with the fact that it's open, the property is open. Okay. I'll try to keep it here for a while. And now I'm going to state somehow I want to state it in this way. I'm going to call it key lemma, although if it's not going to appear so there's going to be two results now that we're going to prove. There's one that I'm going to call key lemma and a proposition. The proposition is that if I take a combinatorial ideal, I can resolve it by combinatorial blowing up. There's going to be a resolution of singularities of it by combinatorial. But before that, I want to make some sort of a key lemma which identifies a property, a useful property of the relation between the derivations and this combinatorial blowing up, which later on we want to generalize to more general sequences of blowing up, which are not necessarily combinatorial. So this key lemma that I'm going to call here, key lemma, says that if sigma is a combinatorial, let me write everything, although if I didn't in my notes. Is a combinatorial blowing up. Then I can put it down. Everyone has copied already. You want to copy. The pullback of the sheaf DE is now going to be the new sheaf of derivations E tilde. This is going to be a key lemma later on. So I want to start with before proving it, I want to start by defining what is the pullback of a derivation, right? And we're going to see, like I'm going to only sketch the proof, but I'm going to call here preliminaries. So the first thing is how to, let B be a point in the center of line, or just a point in M, and A a point in sigma minus 1 of B. So we can, maybe there's a whole fiber, we take one of the points, right? And let X be a derivation, any derivation actually, at the point B. So what we want to define as the pullback, so the pullback of X at A is a derivation, is the derivation, sigma star X, which satisfies the following property. Sigma star of X applied to the pullback of a function has to be the pullback of X applied to this function for all functions at B. Okay. This is the definition that I'm going to take, and I want to look at it at a blowing up, which is not, and a derivation, which is not going to be tangent to the exceptional divisors, to see that there's something to prove, and to see that this definition is actually what can go wrong. And I'm going to do this in a very simple case, typical case, which is, let's take M equals to R2. Let's take E empty, so just R2, coordinate systems. x and y, we blow up the origin and consider the x chart, x equals to u, y equals to uv, right? And let's pull back the derivation given by dx. We pull back dx. So the derivation that we pull back is going to have entries in the derivation in u and entries in the derivation in v. So it's enough for us to compute, first of all, let me do this matter, to compute it over u. So doing this is the same as computing dx over the pullback. U is just equal to x. And now we use this formula. It's going to be the pullback of the derivation of x in x. This is 1. So this is equal to 1. On the other hand, if we try to do this for v, then what we're going to get is the pullback not of x and not of y, but of y over x. And when you do this all together, what you're going to obtain is minus y divided by x squared, which is equal to minus v divided by u. So the actual derivation, the pullback of the derivation is not actually well-defined. It's going to have a pole. It's going to be du minus v divided by u dv. There's a pole here. Right. So this gives us an example of a case, and we see that, that something can go wrong. It's not true that in general, the pullback for any blowing up, we're going to have this equality. But for combinatorial blowing up, the claim is that there's not going to be any pole. And better than that, everything is going to stay tangent to the derivations, to the exceptional divisors. Okay, so I'm just going to sketch it. So, or give the main idea. So after these two observations, this sketch is going to be more or less simple. Right. So yeah, I'm just gonna tell you what is going to happen, right? So suppose that the center, we could always suppose, right, that this was the zeros of say U1, UK, and consider one of the charts, the U1 chart. So the U1 chart, we're gonna write U1 equals to U1 tilde, and then we're gonna have UI equals to U1 tilde, UI tilde for y, for I equals to 2 up until t, uj equals to uj tilde for j equals to t plus 1 up until r, and whoops, not u, vjk equals to vgk for k equals to 1 to s. And now the claim that I make is that if you do this exact same thing that we did here, if you do this as an exercise, like you compute what is going to be over u1 tilde, u2 tilde, just write what it is in the transform, y divided by x and everything, what we're going to get is that the pullback of u1 du1 is going to be u1 tilde du1 tilde minus I should not have used it ing. I'm going to use it out. Equals to 1 to 2 to t u not a l l tilde dul tilde the pullback of ui. Yeah, so Not perfect annotation. ui tilde, dy tilde for I equals to true up until R, and not only T. That's why I'm saying that's not perfect notation. And the pullback of the dvk is just going to be dvk tilde for k equals to 1 up to s. So we see now that if we take the span of these vector fields, it's going to generate, definitely is going to generate ui tilde, ui tilde for every point, dv k for every one of the directions, but also u1 tilde, u1 tilde, because I have a linear combination between these terms here, which is going to give us u1 tilde, u1 tilde. And this is going to prove the lemma. Now, an immediate consequence of this lemma, which is actually what is going to be important for us, is that if we take the pullback of the derivation at I, then this is, so if, let me write it, if sigma is combinatorial, then this is going to be the same as taking the derivation of the pullback ideal. I'm going to be the same thing as doing that. This is going to be an important consequence for later on. And now the second result that I want to talk, which finishes this part of combinatorics, is the proposition here. Our first resolution of singularities result. Which is, and I'm going to say like this, local resolution of singularities holds for a combinatorial ideal if I under the extra condition 1 prime, which is that the sigma lambda is a finite composition of combinatorial local Blanks, of local combinatorial Blanks, local combinatorial Blanks, combinatorial. Local combinatorial Blanks. Let's catch the proof of this result. So this is the.
Sorry, just before we start. So this 1 prime is an extra conclusion, right? Not an extra assumption.
Yeah, so let's go back to the theorem because I'm doing this so that I don't have to write the entire thing. So it means that the theorem here holds, but instead of 1, I'm going to
have.
So here was just a composition of local blowings up, and there's going to be extra thing is local combinatorial blowings up. So there's something.
Yes. So that's a stronger conclusion.
Exactly. Yeah.
Okay, not a stronger hypothesis.
Ah. Oh, you're right.
I see. Because you see. Okay, you see what I mean. Okay.
Yeah, I see what you mean. Thanks.
Okay. Thanks.
That's this. We're going to fetch the proof. So in here, like there are many ways to. So let's just say if we follow the usual way in resolution of singularities, which is built up from a global resolution of singularities, we use what is called. We show a simple result about the coefficient ideals of the combinatorial ideas, and we argue by induction. But I'm not going to define coefficient ideals. The idea of this local resolution, we're not going to define all of the techniques that are used in a global resolution. So I'm just going to give a different proof, which is going to use in a strong way the fact that we can be local. So the proof that I'm going to give is not global at all. It's just going to be a local result. But this is what we need for now. So it's going to be more explicit and very elementary. So the first thing is that, so where do I start here? So first thing is that we may write, find a monomial M such that the ideal I is given by M, and then we have the generators Mi, Md, but with the extra condition, and there is no common term between them. Right, we factor out the biggest possible monomial that we had from all of these MIs. Now, I'm going to argue that the essential case for us is D equals 2. And this can be done by induction on the number of generators. So induction in the number of generators of course, if D is equal to 1, we're done. So we're going to make the induction in the number of generations or generators. So it's enough to consider the case D equals to 2, because if we consider the case D equals to 2, and here we use strongly that we can be local and not global, we may choose 2 of these monomials and apply our induction for D equals to 2. And in the end, the pullback of the idea will have D minus 1 generators. So we may apply induction again. So in here, we are using the fact that it's local so that we can choose. Normally in global resolution singularities, we cannot choose anything. Everything has to be intrinsic. But for local, we can do this. It's not going to pose any problem. So we may choose any 2, make the sequence of lines up that we're going to find here. And then we're going to have D minus 1 generators and follow up by induction in the number of generators. So this is the essential case. And now we may write, in this case, we may separate the U variable in 2 parts, X and Y, such that M1 is equal to X, Y alpha, and M2 equals to Y beta, right? We factor out any term that there could be common between all of them. And since we only have 2, then for sure we can just separate. There's no common term in between them. So we can separate the U coordinate in 2 parts and write M1 equals to X to the power alpha and Y equals to the power beta. Now for a point B, and we consider, which depends on this way of writing, but it is an invariant after all. It can be shown that it's an invariant after all. And this is going to be for us, I'm going to write like this, P of A of B. So this is nothing but the number of exceptional components at B. So it's the number R, right? This is also like when we are doing things that is equal to R. Then the second one, I'm going to take gamma of B. This is nothing but the not the maximum, the minimum. Sorry. The minimum between the alpha and the beta, and then delta B, and this one is going to be the maximum. It's the maximum. Okay. And then my claim, the claim here is, if we choose the center, well, this invariant decreases at every point A in the pre-image of B. So choosing the invariant well is just it's just because I want to leave the general claim as an exercise, and then choosing this invariant, the center depends on the entries of alpha and beta in some way, which I'm going to leave as an exercise. And I'm going to just prove the claim where there's no choice of center there's no reason to choose a center differently, but just to see the computation that appears, I'm going to do in the case that I equals to 2. So x and y are just one variable. We treat the case r equals to 2. So x, y are distinct variables. Right, like this. They are not multivariables. And now there's no choice. We just blow up that center. There's only one combinatorial center that is not an isomorphism. It's the center given by x and y. So we blow up with center v of xy. Consider the U chart, the X chart. X equals U, Y equals UV. Then we have that the pullback of M1 is going to be U to the power alpha, which is also U gamma, where this gamma, and let's note gamma B equals to gamma, U gamma times U alpha minus gamma. And the pullback of M2, this one is going to give us U beta, V beta, which is U gamma, U beta minus gamma, V beta, right? So now two cases, if the minimum between the two of them was alpha, if gamma equals to alpha, then we're done, right? This is alpha minus gamma, so we are factoring off U gamma from both. We're gonna get, we're done. So if gamma is equal to alpha, then I didn't say what the point is, right? Sorry about this. UV is centered at a point A after the blowing up. Sorry about this. Then the invariant here, the gamma A is certainly going to be 0. So we're done. Finish. Otherwise, oops. If gamma was equal to beta, then in this case here, this one became alpha minus gamma, so then we get that M1, we have U gamma, U alpha minus gamma, and the M2 is going to be U gamma E beta. So in this case, and we might not be able to conclude that gamma A is strictly smaller, but it is certainly smaller or equal because beta was the minimum between the two, and it's appearing here too. But the maximum has decreased. Finally, that's the thing that I didn't say. So we made this blowing up. I look at it, one of the charts, I look at the center of this chart. And we made this computation. We said, okay, the invariant has dropped. Now, if we consider any other point of the chart, so that's the drawing that I should have made. We made the extra blowing up with the center. So here was U, here's V. Right? And we fixed our point here. But if we take any other A prime in the exceptional divisor for A prime, the number of terms of the exceptional divisor has dropped. Right? So the invariant has also dropped. So that's why if we take any other point besides the origin of that blowing up, the invariant has gone down. Otherwise, the invariant is still the same. And the first part of the invariant is still the same. It's the same number of exceptional components at that point, but one of the other two has dropped. So infinite number of steps, we're going to get that this invariant has to drop, it has to go down. And of course, if it is if the number of exceptional components is 1, we're done. It's a monomial. And if this guy is 0, we're also done. So eventually, you're going to be done via this method. Okay. Should I do a little pause? Oh.
Yeah. Yeah.
Go ahead.
Did you, sorry.
Yeah, you people want a little pause, maybe we can do a, so afterwards I'm going to start by the inductive statement, like this finishes the part of combinatorics. So maybe let's give 5 minutes, a 5-minute pause, so to restart at 4:15, so that we have time to rest a little.
You said briefly that the case in 2 variables, if we understand the case in 2 variables, it's okay, right? You said something like that briefly.
But you can do the other by exercise, yes. It's
okay, so
it's not
complicated.
It's not complicated. That's what I meant.
Okay, okay.
That's what I mean.
Okay, thank you.
There is something to do.
Okay, right. Yeah, that was my point.
Yeah.
Not totally immediate, I guess. Yeah.
No, I thought that it was a good idea. Like when I was a student, I liked it when I had exercise time.
Right. No, you're right. Yeah.
To give some exercise. So I know that there's PhD students and postdocs that maybe are not could be shy in asking questions, and then if there's something to be done, they can ask. Okay, maybe let's restart, Amana.
It's okay. I've started the recording.
Okay, it started.
Yeah, you can go ahead.
Thanks. Okay, so let's continue. So now I'm going to talk. We finished this combinatorial part. We proved these 2 results, this key lemma and the proposition. And now I want to make the inductive steps of what we're going to prove. And with this inductive steps, we're going to motivate the use of the log calculus, calculus of logarithmic differentials. So let's start here, and I'm actually going to prove the result. I know that this seems like a big simplification, but we prove the result for the ideal generated by one function. The general case, so I'm going to actually write it. So the general case is not actually harder. But it's harder notation-wise. And I feel that the ideas are going to be completely more transparent if we focus on this case, and then it becomes, well, an exercise of generalizing it to the case of where there's many functions, but it's going to be very similar in any case. Okay, so we're going to focus on this, and we're going to step some notation. So I'm going to start so that we can use in a constant way. So I'm going to make here a little. Actually, yeah, I wanted to have that. So let's do like this. Let's fix M is going to be the dimension of our variety, and we fix A0 in M. And I'll come back to this notation in a bit. I'm just fixing the point. More. So let's write here what is going to be our first step. So this is going to have 3 inductive steps, and I'm putting M as a dimension, right? So apart from a family sigma lambda satisfying 1 prime and 2. So recall 2 was that it was semi-proper. 1 prime was that it was composition of local combinatorial blowings up. For every point which belongs to the prime image, let's write like this for now, of A0, either we're done, nothing else to do, or there is a nice normal form. There is E adapted coordinate system. U, V, and I'm going to distinguish one variable W, which is not exceptional, such that the pullback of F is now going to be given by U some gamma, some monomial, which multiplies W to the power D, F tilde, VW, plus E equals 0 to D minus 1, AI UV, which is independent of W, WI. This is the first thing I want to, the first step. Where, of course, this F tilde at A1 is different from 0. These AIs at A1 are equal to 0, and F tilde and AI are in the quasianalytic class. We want that. So this is some sort of weak Weierstrass form. It's not a Weierstrass form because it's not a polynomial. It's not a unit times a polynomial. The unit is here, multiplying W to some big term here, D. Okay. And I want to come back to the notation and just so that we can use in a little bit more free way this. So I want to use this in the notation wise. I want to consider the union of these V lambdas that we had constructed, right? The family sigma lambda was amorphous from V lambda to M. So let's just call this one V1, the union of this A lambda E1, and let's consider sigma 1 as the morph given by, well, V1 to M, such that sigma 1 restricted to V lambda was a sigma lambda. And finally, we also take E1, not going to be a problem later on, with the first pullback of I. Okay, so if with this notation, it becomes a little bit easier to write because now we can just write here sigma 1 as mononomial AI, or there exists a E1 adapted coordinate system such that this happens. Okay, so it's just a way to write it that's going to be a little bit easier. And I'm going to use this notation in the same way for the next step. So now I'm going to fix A1 and I'm going to go over it with the point with a point A2 and with a morph sigma 2 doing the exact same things. It's just going to be easier to restate. But before doing that, I want to just set some sort of claim that this number D here is going to play an important role for us. So I want to set it in a special way. I want to set the following. We set me at this point A1 of E1 of I1 equals to D. Now this setting here is a little bit, has to be said. It will be an invariant. Because in here, I'm not using any dependence on the coordinate systems. If we consider the minimal in respect to all adapted coordinate systems. But as we're going to see later, there's going to be a better way to define this invariant, just in terms of the log differentials. And we're going to get that it's an invariant, like it's going to be an invariant in a very direct way. We don't have this kind. We don't have to use actually this kind of thing. I just want to give it a name for now in inductive steps, and afterwards, it's actually going to be a precise invariant that we're gonna keep tracking these inductive steps. But for now, it's already enough just to look at this D here.
So
now the
invariant. So, sorry, André. So invariant means independence of the coordinate system, right?
Yes, that's what it means. Yes.
Okay. Okay. Thank you.
Yeah. So in here I can do it artificially by taking all possible coordinates change and fixing it. But we're actually going to see that there is going to be an intrinsic way that only depends on the derivations. So the step 2 is the following. So apart from a family, and now I'm simply going to call sigma 2 satisfying 1 and 2. So in here, we're not only doing combinatorial points up. I didn't say that. Fix A1 in V1. Again, the problem. For every A2 in the prime image of A1, we may suppose, nothing now. we may suppose this normal form is actually better. It's going to be given by some u to the power gamma, monomial. It starts the same way. And now it's going to be a new alpha I, so some monomial, multiplying bi uv, wi, I from 0 to d minus 2. So there are two differences here. Did you go? Yeah. The d minus 2, before it was d minus 1. And now we have these terms here instead of the AIs. So I need to precise what are the difference here. And where again f tilde of A2 is different from 0, it's a unit, and either bi of A2 is different from 0, or there's nothing there actually, or bi was equivalent of 0. And of course we have the last coordinates and the last pi's. F tilde and bi are in the set. So we're going to have this form of preparing the normal form that we have here. So we obtain some Weierstrass form and then we prepare it. It becomes like this monomial times wi. And finally, so fix A2 in V2. And the last induction statement that we're going to make, and I'm going to make in the next page. Although it's quite, no, it's, yeah, I'm going to do in the next. Yeah. So again, apart from a family, let's call it sigma 3, satisfying 1 and 2, it's going to be very close to being combinatorial, but not really. There's going to be it would be combinatorial if W equals 0 was an exceptional divisor. So we're going to actually enforce this, as we're going to see. Almost combinatorial, but not exactly. So apart from a family which is a local sequence of lines up, which is semi-proper, for every A3 in the preimage of A2. Now, this invariant that we just defined, this D that we just defined, so here it's going to be E3 is going to be strictly smaller than the invariant at A2. So let's try to understand what this means, the consequence of that. So we're saying that after, so let's go back. So we started with a sequence of lines up that gave us a D here, a D that appeared here. And we said, well, apart from making change of coordinates, we can assume that its minimum with respect to its change of coordinates, it's going to be an invariant we call by this name. Now in the step 2, and I can say this, we are not going to change this D. So, and maybe this is going to be helpful. I didn't write in my notes, but I now realize that it could be helpful. This is equal to A1, E1. We didn't change. The D is going to be the same. We just keep this D the same. And now, by using the step 3, we get that it decreases. So now the D decreases. If it goes to 0, then we are done. Because if D is equal to 0, it means that this function is just U gamma times a unit. So it's a monomial. Otherwise, if this is positive, we can just apply step 2 and step 3 once after the other up until we're at most d times step 2 and step 3 up until this invariant has to be equal to 0. So this shows that if we do this if we prove these 3 steps inductively, we are going to be able to finish the proof. The proof is going to follow by first applying this, we get our normal form, we prepare the normal form, we decrease the invariant. We prepare the new normal form, we decrease again the invariant. At most d times, we're going to get to 0. If we get to 0, this is a monomial. Okay, so this is the plan.
Andre?
Yes.
Sorry, isn't this A3 in sigma 3 minus 1 of A2?
Thanks. Ooh, what's not? So my board here doesn't like when I make mistakes, and it wants to show to the world that I made a mistake. It doesn't allow me to change from time to time to the eraser. For some reason that I don't get it. Yeah, but you're right. It's sigma 3.
Thanks.
Oh, now I got a more serious problem. Now it worked. Right? Yes. Thanks. Thanks, Kyle. Okay. Now it works. Okay. I probably touched something in there. Anyway. I don't know. I just want to, before turning to the last point, I just want to make a little comment about the logic and about what we can do and what we don't do here, right? So, how much space do I need for this drawing? Maybe we can do it here, so let it big. So we are starting with a point B in the beginning, and I just want to make a comment about this whole step process, right? And we applied one of these steps. We applied the step 1. Okay, so we got some covering here. And we have the fiber of B. The fiber. Sigma 1 minus 1. Oh. Now, the logic that we are using is the following. For each point A1, we are saying we're going to find a finite family of local points up, which is semi-proper, and that if we compose all of this, like the logic that I'm going to use here is a composition of the same logic. But let's say that after this composition of this local points up for every A1, I am able to get, I'm able to get a monomization of I. So after this sequence, I'm able to get a monomization of I. And sigma 2 composed with sigma 1 star, sorry, the opposite. Sigma 1 composed with sigma 2 star of I is monomial. Now, the comment that I want to make is that we did this for every A1 and we cover it, but now being monomial over the exceptional divisor, over the fiber, is a local property. So this is actually true for open sets. And we do know that if we take here, did you check it? If we take here a sufficiently small, relatively compact open neighborhood, then it can cover by relatively compact open neighbors here, because it's semi-proper, whose image is going to be this set. So what we are saying is that the pullback of this entire set over here is going to be monomial. So actually, when we say that we fix a point and we have resolved the singularity to obtain that is monomial, didn't say it completely. In sigma 2 minus 1 of A1, local property. We actually get that it's going to be monomial over an open set of this A1. And now we can do the same trick, like the same logic again. And we say, okay, so there is a way to cover here with some open sets where this property is still valid, where we still enable that over this U set, over this red set, I'm still able to resolve, and which is sent to a relatively compact open neighborhood of B. And I can cover by a finite number of these little balls. So it's because of that that the composition of this argument is enough. So that's why I'm not saying the size of the open sets in each one of the steps. I'm just saying I will fix a point and I will continue, because in the end I can always use this the semi-properness at the end and the fact that the being monomial is a local property in order to get the open set that we wanted in the beginning. So this was a comment that I wanted to make about the induction strategy and why we are able to always fix a point after the sequence of lines up. But we have to prove for all points after it, not so that's why it's for all points. Yeah. Okay, so now that I talked about this logic, I want to talk a little bit about log differential calculus, and in particular to define this invariant here, but in an intrinsic way, so that we see what is going to play a role. So part 3. So the center here is some sort of analogous of the order of an ideal when we consider all of the derivations. So we're going to do the analogous of it. Privileged. You here. Now the notation is going to be a little bit heavy, but I wanted to do it. There's ways to do it less heavy, but I wanted to keep it so that the exceptional divisor does appear here. And we know that this will depend on the exceptional divisor. Where ek plus 1 of E is equal to the previous one plus those derivatives applied to it. So it's, if you are used with the usual differentials, like this is the way to define the order of an ideal. You just derive sometimes, and at some point it becomes a unit. The point that it becomes a unit, this is the order of the ideal. So in here, we're going to do the same, but we are going to only take the derivatives which are tangent to the exceptional divisor. We're going to keep track of this exceptional divisor. And since we are quasianalytic and there's no sphericity, we're also going to consider that U infinity of E be the sum of UK V for K in the number. We define this ideal here. And now that we are in this situation, we are ready to define what is the invariant that we're talking about. We say that, so like this, to use space, there's a lot of space. So the invariant we're going to define, like a given A, and A of I. So that's why the E was appearing there, because it's going to depend on the derivatives here, depend on E, is going to be the mean of K in the naturals possibly infinity, such that we have space, such that we have stabilized. So if we take the germ at that point, this is going to be equal to the germ of the infinity one. That point, right? So if remark, if Q is Noetherian, if QA is Noetherian, if QA is a Noetherian local ring, for example, if Q is an analytic, the class of analytic functions, then μA of E is always smaller than infinity. It's always finite. In the quasi-analytic case, we don't know, right? We don't know if it's Noetherian, so we don't know if the sequence of ideals is going to stabilize or not. It's not going to be. So we might have to admit the case that this invariant here is going to be infinity. And part of the proof of the things that we're going to do, maybe not today, we'll see how far we're going to get, is that this invariant that we're defining here is the same one as the one that is appearing here with this D, with this Weiss transform. Let's get there. So let's start by some examples of what is going on. So I wanted to do, right. So the first thing is that why this invariance is not, why did I say that we need to make change of coordinates, right? Because we might have chosen that. So take I equals to the function f, where f is going to be w to the power d as before, but plus v. 1. So in this case, if we just derive once, we're going to obtain 1, right? Because note that dv1 of f, this is equal to 1. So when we sum, when we take I plus d, sorry, I put it below, of I, this is for sure just going to be the idea 1, which implies that this invariant that we are looking at, the me E at the point A of this ideal I, is just equal to 1. Right? After one derivation, we stabilized. 1 was not in the original idea, but 1 is afterwards. So after one derivation, we stabilized. So this is the first easy example. Back to the second one. Now the second one, I wanted to take the case of the normal form and to see what is going to happen. Okay? So I'm going to take it I equals to f, where f is going to be exactly as in the normal form that we were considering before. And now my claim is that this invariant, whatever this invariant is going to be, is going to be smaller or equal to d. Okay. It's going to be, well, we're going to see, it's actually, we can choose coordinates so that it's going to be equal, but for now, let's just prove that for whatever coordinate that we have, if we obtain this coordinate, this normal form, then it's smaller or equal to d. So the proof of this is simple. Note that the d derivative in respect to w of f is simply u to the power lambda times, well, f tilde plus some term which is of order 1 in W. Right? So it means that u lambda times, this is a unit, right? Because this part here is 0 at A, and this part here is non-zero at A. Sorry, here there is a d factorial. It doesn't change much. Okay, so it's u lambda times this. And from here, we conclude that u lambda belongs to the ideal u, e, p. So that we know. Moreover, u lambda needs to be contained in the, we know that it is two little remarks. Remark 1, u lambda divides.
Andre, I'm sorry, I'm a little lost.
You're lost of what we're going to do.
No, but I'm also like, I don't understand why any element from the sum would survive the derivation. No, the sum completely vanishes in the derivation, no?
Because they only depend of order I in W.
Yeah.
So if d times in W, these terms here are all 0. Is that the
Yes.
question?
Yeah, but why? Yes. So the question is why there would be anything else than just factor d times f tilde.
W appears in f
Bracket.
tilde too.
Okay, sure. Oh, W appears in f tilde. Okay, that's the answer. Okay, thanks. Okay.
Why this? Yes, because it depends on W. So yes.
Okay.
Again, the same problem. Let's continue. U lambda divides x. So we note that u0 is contained in u lambda. And 2, u lambda is invariant. It's a monomial, so it's invariant by the derivations. So if you look at the chain that we had there, so this one is contained. The next one, since this is containing it, like when we derive, it's going to be containing itself. We know that this one is also containing u lambda. And therefore, ID is also containing u lambda. But it also contains u lambda. So we conclude that ID is equal to u to the power lambda. Therefore, which is invariant by which is invariant by these derivations. So we have concluded that this is smaller or equal to d. So this proves the claim that we said. Okay. So now with these two examples in mind, I just want to finish with some key properties that we're going to use in the next time. So I'm going to call property A the following. Let sigma of n e tilde me be a combinatorial going up, be a combinatorial going up. And let G be the prime image of I. Then the claim is that GK E tilde is going to be equal to the pullback of ik for all k and in particular for all sorry. No, I can see like this for all B in M for all A in the preimage of B, the invariant can only drop of tilde A of J smaller or equal to the invariant of B E of I. Right. And the proof of this key property is the key lemma, because the key lemma told us that combinatorial blowing up is going to keep the derivations, right? So the proof is direct from the key lemma about combinatorials, right? Because we just said that I'm going back so that I can show in definition, so that the pullback by combinatorials blowing up of the derivation is going to be the new derivations, right? Which are tangent to E tilde. So this definition is going to just pass one term at a time, and we're going to obtain that the new sequence is just going to be the pullback of the old one. Anything else? No. So this is the first of the properties that I wanted to talk about. Combinatorials is going to preserve this invariant and also preserve the sequence itself. There's something important in this. Now the second part here. Oh wait, we finished at 450, right? And not at 5.
Yeah.
I made this mistake. So right. Okay, so maybe let's stop here so that we don't pass too much time. And in the next time, I'm going to talk about what are the key properties, and then I'm going to state all of them without proof. Can I pass 2 more minutes so that I can state all of them, and then next time I prove them?
Sure.
Okay, let's do that. So suppose that I infinity E is monomial. First remark, an obvious remark here. If the invariant is 0, then I is monomial. Second one, for all A, the invariant is actually going to be finite. So it's saying that if we get that this last one is monomial, then all of them are going to have finite invariant, not infinite. And last, which is the property that I wanted to finish it, if μAE is equal to D, bigger than 0, and our ideal was, so there's another version for general ideal, but just in the case of the hypersurfaces, then there exists the adapted coordinate systems such that U lambda WD F tilde AI UV WI F tilde at A equal to 0, AI at A equal to 0, F tilde and AI magnetic field. So the next time I'm going to, so these three properties are going to be simple to prove, and they capture more or less everything that we need in order to prove then all of the statements without not that much computation, as we're going to see. Not much computation. So these are the properties that we're going to use, and we're going to restart next Monday. So thanks a lot, everyone. We'll stop here.
Thank you, Andre.
Thanks.
Thanks, Andre. Very nice.